for example, let's say that our outflow was 1.37. Okay? Let's say, for example, that we have an agreement. The Pale Subbasin has an agreement with the Chinwin Water Users Association, whatever, just making it up. And we say, we will give you 1.37 cubic kilometers of water every year. So that means the outflow is committed, 100% committed, right? So this is 1.37, this is 1.37, right? So that means this is 0. 0, 0. Okay, so then the politician, you're the water expert. Okay, who am I going to think of? You're the water expert, okay? So the politician, the president, comes to you and says, I have $1 billion. $1 billion, and you're the expert. You have to decide, you have to tell me how I should spend that $1 billion in the Pale Subbasin. And I say, I really think that it would be a good idea to build new reservoirs, store more water, and grow more rice. Okay? But you go and you do the water accounting, and you see, okay, based on our treaty with the Chinwin Water Users Association, whatever, all of the water is committed. And most of what's being depleted is already beneficial, isn't it? We have 3.52, and of that, 3.36 are beneficial. So what do you tell the politician? What do you tell the president? You say, yes, let's build more reservoirs. Or you say, no. Look, Mr. President, or Mrs. President, let me show you the water accounts. This would be a bad investment of $1 billion, right? Because you know what? We're going to end up taking the water from the people that we committed the water to give already. They're going to be unhappy. We're going to have another war, right? And we just wasted $1 billion. But as it is now, that water is uncommitted, isn't it? So now the president comes to you, choose a new expert, male expert this time. You're the expert. Yes. So the president comes to you now and says, okay, I have $1 billion. What should we do in the Pale Subbasin? How can we improve water management, food security, economic productivity, right? And we have a lot of uncommitted outflow. So what do we do then? How do we, what is your recommendation to the president? Maybe we should, you can say it in English. Okay. And the president says, what do you mean by that? So practically, how should I spend $1 billion separating the water? Or do I need to build some new infrastructure? Do I need to build some new, how do I invest this money? New canals, better seed, what should I do? Does anybody else, I don't mean to put one person, we all have to be the experts together. So together, what do we tell the president? We get together, we have a meeting, we call the Myanmar Water Accounting Expert Group together. We come together, all 30 of us, and then we have a discussion about it, right? We should do this. What should we do? What do you guys think? We have $1 billion. Okay, I get 30 million, you get 30 million, you get 30 million. Okay, we're done. Yeah. Okay, we've taken the $1 billion. We each have 30 now. Thank you, Mr. President. Is that what we agreed to do? That's not what we're going to do. Doesn't need more people to take the money in the pocket. No, we don't need that. Okay. So what should we do? Yeah, because we have uncommitted outflow. Where does this make us any food? Does this make us any money? Does this help the domain? I mean, not really.
ဒီဖက်မဲ့ထဲမှာကျွန်တော်တို့ထွက်ထားတဲ့နိုင်ငံတွေပေါ့ဘယ်လောက်ရှိတယ်လဲဒီ accommodated outlook စီးထွက်တဲ့တော့ဒီအော်ဘောဒီလိုလိုမျိုးမျိုးရင်ဓမ္မချောင်းတွေကစီးသွားတဲ့ဥစ္စာချင်းလေးတွေဝင်သွားတာပါလေအဲ့တော့ဘာအတွက်သုံးနေတာအတတ်မှတ်ရှိပြတယ်ရှိလို့မရှိသေးဘူးဟုတ်တယ်နော်ချောင်းဟိုဒီတော်စီးတာတော့မရှိရှိပဲဟိုအဲ့တော့အဲ့ဒီဥစ္စာမျိုးတို့ဒီအဝင်အားလုံးတွေကနေပေါ့ဒီပြည့်တဲ့ဥစ္စာလည်းထည့်ကြ accommodated အောက်လို့လည်းမှာအခုတည်းကအများကြီးကြံနေတယ်။အဲ့ဒါကိုကျွန်တော်တို့အသုံးချဖို့အတွက်အခုလုပ်ရင်ကောင်းတယ်။ဘယ်လိုအသုံးချအကျိုးရှိဆုံးတွေ။ဟုတ်ကဲ့။ဟုတ်ကြားစရာမရအောင်။ကြားပါများ။ဘာသုံးချအောင်လဲဒီဒီမှာစားပါတော့ချောင်းပါတော့တိုင်းမှာချက်ပြေကိနေတော့ဗျာဟုတ်ကဲ့ဟုတ်ကဲ့ဗျာဟုတ်ကဲ့တော့ဘာလို့ဟုတ်ကဲ့အဲ့ဒါတော့တော့ okay so like many of them is that okay we cook like the gas cost for irrigation and also how the idea
Yeah, I think we can do it. We'll try to think of an example. I'm trying to think of a way to illustrate this. Okay. I think we can think of it like this. This is how much water we have to kind of work with, right? This is how much water we have. It's the amount of precipitation plus any changes, plus or minus changes in storage. That's kind of what we have to work with. It's kind of like our income. It's like we have a job and we make $100. It's like our income. We don't have more than $100. We don't have less. We have $100. And then we, as water managers, have to decide how we spend that $100. Okay? So this over here is like the spending, right? This is like your expenses. And this over here is like your income. Remember, this is water accounting, so I'm trying to link it back, okay? So right now we're spending, of that $100, we're spending like 70 of it for depletion and like 30 of it for outflows, right? And what are we getting back from that investment, right? So for outflows, we might be getting back maybe some nice, like a nice stream that we're working on a tone. But is it okay to maybe take 10 of those 30 and then invest it in growing more food? And maybe then we only have 20 here. Is that okay to do? Is that a good decision? The president give you the $1 billion? We don't know yet because we don't know enough about the stream and how that would impact the ecosystem and all that, right? But let's say that there's enough water to take some. The goal would be is to take from our uncommitted, utilizable or non-utilizable water and move that water up here to benefit the process. So you want to change the way we're kind of investing that from uncommitted to benefit the process. Okay, so that's the key.
တော့ဆရာတို့ပြောရတဲ့အခါမှာလေနောက်လို့အခုချောင်းထဲမှာစီးနေတယ်ကြီးအဲ့ဒါချောင်းထဲမှာစီးသွားတယ်ကြီးအဝင်တွေကတစ်စီပိုင်းတစ်ခုနော်ကျွန်တော်တို့နားနေဝင်ပြီးတော့ပြန်ပြရတယ်နားတာဟုတ်ပြီဒီနေရာရတယ်ဒီနေရာတွေကနေပြီးတော့အောက်ဆရာကျွန်တော်တို့သုံးနေပြီးသားအောက်ဆရာဆောင်းပတ်တရားပဲကိုကသုံးနေပြီးသားအားတော့တော့ကျွန်တော်စားဖို့တော့ဟုတ်ကဲ့အဲ့ဒါဝိစားနဲ့ဒီကားနဲ့ဒီအဲ့သုံးနေပြီးသားအားဒီဘက်အောက်မှာကြံနေတဲ့30လေးကနေကျွန်တော်တို့ဆယ်ကောင်တော့ယူလိုက်ပြီးတော့အဲ့ကိုယ့်ရဲ့နားကိုသုံးနေမှာထည့်တယ် အပြည့်ပြပါပေါ့တလားမှာခိုင်းလို့သမင်းနဲ့မစားနေတာတော့လက်ပိုစားတယ်တော့လက်စားတော့ဗါလက်စားမရပါနဲ့သမင်းစားဖို့ကသဘာဆန်ရှိပါတယ်အဲ့တော့သဘာဆန်စိုက်တဲ့အထဲမှာဖြစ်စီထည့်ပြီးတော့ရောင်းလိုက်ရင်ရတယ်တော့ဆရာတို့ပြောခဲ့တဲ့အထဲမှာပဲကြံခောက်လိုက်မယ်မလုပ်နဲ့တတိသားနေလက်စီသားသုံးသီးသားဖြစ်ဖို့တော့ဒီသေးလုံးလုပ်ရတယ်နော်ဒါကအဲ့လိုထည့်သုံးလို့ရတယ်ဟုတ်
So what is the one thing on our accounts that's missing still? We're missing one number still. Aren't we? Yeah, and not just groundwater, right? We don't have anything about that. We don't know anything about what are the four possibilities for changing storage, changing groundwater, soil moisture, reservoir, snow or ice, right? We don't have snow or ice. We do have reservoirs. We do have the soil moisture. We do have the reservoirs, right? We have the groundwater, reservoir, and soil moisture. Okay. Now, soil moisture. I can make a graph. I'm going to make a visual graph. Okay. Soil moisture after the monsoon, when the monsoon ends, right, is high, isn't it? Soil moisture is at the peak at the end of the monsoon. Okay. And then as you go on, the soil moisture goes down and down and down and down, and it gets to be the very lowest just before the monsoon starts, isn't it? Like right now. Maybe late April, early May, it's at the minimum. And then it starts to rain again. And then it comes back up to where at the end of the monsoon is the same as what we started with. Pretty close, don't you think? It's saturated again. The whole soil profile is filled up. So if we look at remember, we're interested in the change in these reservoirs, right? The change in these storage functions. So if we started here, and then it went down through the dry period, back up at the end of the monsoon, and we end here, what's the change? From the start to the end, what's the change? No change, right? There was fluctuation within the year, but if you look at the end of the monsoon 2017 to the end of the monsoon 2018, it's about the same. If we look at from the end of the monsoon 2018 to the end of the monsoon 2019, also, there won't be much change. So soil moisture over the period, see we're doing this for the whole year, aren't we, for all 2019 to 2018? Can we assume that soil moisture change over that whole year is 0? Yes. Yeah. Okay. If we do it every month, can we assume that? We can't assume that every month. Because maybe May it goes down, but then June it goes up, July goes up, August, September up, and then down, 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 down. So each month is changing. But over the course of one whole year, it ends up in the same spot. Right? So okay, so then we can say, okay, soil moisture, we're not gonna ignore we're gonna ignore that one. Right now. Okay? So soil moisture goes away. So then we're left with two things. Groundwater and reservoirs. Okay. So reservoirs, how do we calculate the change in the area, the volume, the change in storage? Can I erase this? So how do we calculate the change in storage for a reservoir? Can someone come up and anybody like to draw a picture or explain that? How we would do that?
No. Đi lòng nhà đi. Lòng này. Cô đi nè. Đi lòng nhà có dùng là gì cũng có. Xem nhớ mà hỏi nhau. Xem nhớ không? ရလူများတယ်ဟုတ်ပါသေးတယ်အဲ့ဒီလည်းစားဒီလိုမျိုးတော့တော့ကလည်းကြာပါဘူးကျွန်တော်ကလေးဟိုပါလေသိဘူးပေါ့နော်တော့ဝဲတော့လို့နော်
So, um, we draw a very simple So, let's say this was the river here, it used to flow like this, and then we built a dam here, right? And that built up the water back here. So this is all water now. Okay? I'm going to make a cross section through here. Is that okay? Like, look at it from the side. I'm going to slice it and then look at it from the side. So maybe this is now the earth. Dirt. And we have our dam right here. Okay. And we have our does this picture make sense? So this is like looking at it from the sky, plan view. Okay, so we have the rivers coming in to a reservoir. This is our lake. And then we have a dam, and then the river continues out like this. Okay. So this can be. Can't this change in storage here? This reservoir? How would we calculate the change in storage here for our reservoir?
ဒီလုံငန်းကဒီမှာဒီအထက်အကျပေါ့လေပြောင်းလဲဖို့ပိုတော်သားတွေပမာဏကိုပြတ်တယ်
Can we make a domain? Can we do a water balance? Let's make a domain. Where is our domain for this? Okay, let's make our domain like this. Okay, this is our domain. Okay, so what is our water balance? In equals out plus change in storage. Okay, so what is in? Okay, got something. Existing all sorts of stuff. We have surface water, groundwater, we have house, groundwater. And that's the stuff. Okay, so in is E.
ဒီတော့ဘာလဲအပ်
To groundwater in plus. Okay, and then equals. Can I make this? I'm sorry that I'm using Q. Yeah, I'm sorry to change this, but what I'm going to do is I'm just going to say GW in and SW in. And then we have GW out, SW out, and yep. And is there any transpiration?
No transpiration.
No, we can just call it E. And am I missing anything else?
ဒီ
Well, isn't that what this is? I have to change these now too. Isn't the secret just groundwater out? It doesn't have to be going here, it could just be going here. It's out of our domain, right? See that one arrow represents, will kind of flow this way, but also flow this way. Groundwater. So this is our water balance. And we rearrange, whoa, missed something. Yeah, so we have to have change. Okay, that's the whole point of what we're doing. Okay, so can we rearrange this to get just delta S by itself? So delta S equals, can we go, I'm gonna list all these ones and then we'll take off those. P minus, first I'm gonna add plus GWN plus SWN minus GW out minus surface water flow out minus E. Okay, wow. We can solve for delta S like that. And so we have some uncertainty in P. We don't know it exactly. We have uncertainty, we really don't know this one. This one is, we can measure, but it's hard. Probably don't have data. This one is very difficult to measure. You have to probably model it. This one, we can measure. Evaporation, also difficult. We just talked about evaporation. So the uncertainty in each of these terms is big. So can we use this to solve for delta S and be confident that we're getting the right answer? I don't think so. Because we don't really know any of these very well, so we're definitely not going to know this one very well. All of the uncertainty in these terms ends up coming together into the uncertainty in this term. Okay? So the uncertainty in each individual term gets compounded, comes together to affect this one. This is not a good idea. For a reservoir like this. Because the other thing we do is we can just measure this, right? We measure the level. We call it H, right? In meters. And we do something about this area, maybe. So let's say the area changed from this was A1 when it was down low, and then let's say that the level went up here now. Now my new level is up here. My area increases like this. This would be A2. Right? And we have some change in height. Right? We can delta H. Okay? So can we figure out the volume of water that changed if we know this information? The actual, like this amount of water here. Over this whole area. We figure that out?
Yeah.
We can do it, can't we? Yeah. Yeah. It's probably something like the area, the average of the area is probably, so like A1 plus A2 divided by 2 times delta H. Wouldn't that give us roughly the volume? Assuming a linear relationship between these two. Yeah. So maybe tomorrow we'll include some of this data in our water accounts. Okay? So that's surface water. And then how about groundwater? I'm going to erase this. Is that okay? Nobody wants to take pictures. It's really beautiful. It's very actually not beautiful. So I'm going to erase it before someone documents this. So who knows how to calculate the change in water volume for groundwater system? I know our hydrogeologists know this one. So I really would would like to sit down and have someone come up and teach us this. Maybe you can explain that. So this, what we're after is the change in groundwater volume. How do we measure that accurately? I'll just draw a picture. Yeah, I'll draw a picture and then I'll ask you. Okay. So here's the picture. Okay. We have, make it very, very simple. Let's say this is our domain. So I guess in our domain, I'm making it kind of a box to make this easy, but in our domain we have, let's say this is the Chinquin River here, right? And it flows along the edge of our domain. So we have the South Yama and the North Yama, right? But now I'm making it three-dimensional. So now we have some groundwater system, right? And just, we're going to make it very, very simple. So the groundwater, let's say the water level is right here. Okay, so this is that's my groundwater level. You see, so this is all water. It's filled with, it's rock, it's sand and everything, but all the space between the rock and between the sand is filled with water. That's called an aquifer, right? So this is our aquifer. And this is called the unsaturated zone. And then down below this line here would be the saturated zone. Okay? So, if my water, maybe I put in a whole bunch of wells now, right? So I put a well here and a well here, and I start to pump the water. And I lower, so this is my H1, it's this right here. Okay? And then let's say I lower it to where now this is H2. Okay? You see, what is the area of our domain? Area 4, 5, 6, 0 kilometers squared, right? How big should we make our change here? Maybe 10 meters? 5 meters? How far down has our water table gone? You're just making it up. Make it easy, 10? 10? Okay. So let's say this change here. Is this is H1, H2. So delta H equal to yeah, so we should do this one minus that one, right? So it's going to be negative, isn't it? Yeah, okay, so it depends on how we measure it. Okay, let's just say 10 meters. We know the sign. 10 meters, okay. So then my question is for the water accounts, I need to know my delta S, right? So it's not so much all this water down here, it's this difference, right, in water. So when it was here, there was a certain amount of volume, and when it went down here, there's a certain amount of volume. I need to know the difference, right? So this is where I would like to sit down and then let someone else teach this part.
Yeah.
But I know there's the hydrogeologist in here that can do this. So.
ဆရာများတယ်ဆရာများပဲတယ်ဘလို့တက်မလဲဆိုတာလေးကိုဆက်ပြီးတော့ကျွန်တော်တို့ရှင်းပြပြီးပါရတယ် data S လေးကို storage ကပြောင်းလဲသွားတဲ့ဟာလေးဒီ data ပဲနော် Oh,
Okay.
so we will like just multiply the area and the generation.
Yeah? Really?
Yeah.
Wait a second. That's too easy. Is this a big tank? Is that empty? What else is in the tank with the water?
ရေကန်ကြီးပဲလားကျွန်တော်အခုဟုတ်တယ်ရေကူးကန်ဒီမှာရှေ့ထားတာဟာဆိုတော့ရေတပေရော့တယ်သုံးတယ်နဲ့တွက်လို့ရပါဘူးရေကြီးပဲလားဟိုမှာအောက်မှာ
Soil. Fire. Sand. I don't know.
ရေနဲ့ဘာတွေရောနေ
Sand.
တဲလို့ဒီပေါ့နော်တောက်တုံးရောတောက်တုံးလည်းရှိရင်ကြီးပါတော့နော်ပြုတ်လာတဲ့ရတယ်လည်းရှိရင်ကြီးပါအဲ့ဒါတွေကိုဘယ်လိုထည့်ထွက်ကြလဲကျွန်တော်မထွက်တော့အဲ့တော့ဒီတွေ့ရမှာလားနှုတ်ရမှာလား
Soil ရဲ့ဘောလုံးကိုပြန်လုပ်
ဗျာ
အဲ့ဒါက soil ရဲ့ဘောလုံးကိုပြန်လုပ်ပြန်
ဖိုင်ပေါ်လို့ဟုတ်ကျန်ဘယ်လိုယူလဲဆရာ
H1 H1 ညာ
ဟိုစံပယ်တွေထုတ်ပါဒီတိုင်းတိုင်းပါ
ဟိုကျွန်တော်တို့က soil ရဲ့ဘောလုံးကလောက်ရှိနေတာသူကသူ့ရဲ့ဘောစံတစ်ခုကိုပြန်စီမှာသူက2.6ရှိနေတာပေါ့
ဟုတ်
အဲ့ဒါလည်းဒီကူကပြန်လာလောက်ရှိတယ်ဒီကဘောလောက်ရှိတယ်သူက soil ရဲ့ဘောလုံးပြန်လုပ်ပြန်
ဟုတ်
ဒီတိုးတဲ့H1 H2 ပါတော့တာဘောလုံးမှန်တယ်သူကမှ soil မှာ
ဟုတ်
အဲ့ soil ရဲ့ဘောလုံးကဈေးရဲ့ဘော
ဟုတ်
Okay. So if you think of this volume here, it's not all water, right? It's a mix of water and sand and rock and whatever else, right? And we have a specific term we use for the ratio between the water that you can get out and then the rock and the sand and everything that stays behind. We have a word to call that. Yeah.
my ratio
So there's a couple different ones, right? So one of them is porosity, right? The porosity would be the total, here, right here, water pores all here. So pore, the pore means the space that water can be in, right? So the porosity is the ratio of that space that the water can be in divided by the total volume, right? Okay, so that's porosity. But then, so here's my question. Okay, so imagine that I fill this bottle up with soil. Okay, let's say it's like gravel, big rocks, like bigger, maybe like this kind of gravel rock. I fill it all up, and then they say, okay, my porosity for this bottle is 40%. So this is 1 liter, isn't it? So it's 1 liter. So I fill it up with rock, and then my porosity is 40%. So how much water can I add in before it gets full? 400 milliliters, right? Yeah. Okay, so I pour in my 400 milliliters. Perfect. It's right at 1 liter. Perfect. And then I open the drain. I'd say I have a drain. I open it up. How much water comes out?
not really on
But remember, this is gravel. This is gravel. It's like bigger rocks. Almost 400. There's a little bit of water stays caught on the rocks, right? Some capillarity forces that are holding it, but for the most part, the pores between the rocks are big, right? So most of the water, when you open the drain, comes out. Almost 400 milliliters, right? Okay, now I change this to sand. Smaller particles, but still pretty big, but smaller ones. So I fill this up now, and maybe my porosity is still 40%. Let's say it's the same, right? It might change, but just to make this easy, 40%. Okay. I fill up, how much water can I pour in? 400 milliliters again, right? And then it's full, and then I open the drain. How much water do I get out? Something less. Yeah, we don't know, but something less. Not as much as we got with the gravel, right? Okay, now I put soil in there. Mix of silt, a little bit of sand, a little bit of clay, just kind of a loam, maybe kind of like a regular soil. Okay, 400 milliliters, and how much do I get out? maybe I only get like 300, or maybe I only get like 250, right? Then I put clay in here. Okay, so I put clay in, I put the water in, I pull the plug. Yeah, it'll be very slow, but also it'll be very small. Even if you give it all of time, the clay is so small, and it's actually charged, right? It's negatively charged, so the water actually sort of has this attraction, right? And it doesn't want to let the water go, right? So that water is really caught. So even though the porosity was the same in all those examples, the amount of water we get out, if we let it drain by gravity, is quite different, right? What do we call that? There's one term that we use. There's porosity. That's the first start. And what do we call that when we drain the water? Okay. Permeability means, I think, something a little bit different. That's kind of like how it flows through the material, right? Isn't it something to do with the yield, the specific yield? Maybe you guys use a different word. Maybe you use permeability to mean this. I think we use permeability to mean it's something a bit different. You guys heard of specific yield? Specific yield? You heard of that? That's exactly what we were talking about. So specific yield, the definition is if you fill up this 1 liter with that material, you saturate it with water, and then you pull the plug, how many milliliters of water do you get out? And then you make a ratio. So you do the ratio of, so like if we get 200 milliliters out, we take 200 and we divide it by 1,000, so it's 20%, or 0.2. Specific yield is 0.2. Okay? If you have clay, maybe the specific yield is like 0.05. If it's like gravel, maybe it's like 0.4 or something like that. I'm just making these numbers up. This is okay. I'm going to look it up real quick. So we'll just come up with a table.
Maybe in the meantime,
Yeah, please explain. Yeah.
အခုကတော့အဓိကဒီကဘယ်လောက်ပြန်စိတ်ထွက်သွားလို့ဆိုတာလေနော်အလုံးသားပြပြတာအမြင်နဲ့မြင်တာပြီးသားပါဒီဒေတာဒီမှာဒုရတစ်ခုရှိတာဒုရတစ်ခုတည်းကိုရေဖြစ်ရေမဖြစ်ခင်မှာအဲ့ဒီထဲမှာရှိတဲ့မြေမျိုးစားပေါ့ကြောက်တော့အကြီးကြီးတွေပဲရှိနေတယ်ဆိုရင်ဖြည့်သလောက်ထည့်သလောက်ပြန်ပြီးတော့ဖတ်တဲ့ဥစ္စာကြီးဖတ်ရရတယ်တော့ကတ်နေရတဲ့ရှိကတ်နေတဲ့ကြောက်တော့ကတ်နေတာလေးကြီးနေတယ်ဓာတ်တွေကသူဆွဲအားကြောင့်ပေါ့နော်အဲ့လိုမျိုးပဲနဲ့နည်းနည်းလေးသေးတဲ့တဲမုံတောက်ခဲ့တဲ့သေးဆိုရင်ကတ်တာနည်းနည်းလေးပို့ပြီးတော့ရားလာတဲ့ကြောင့်ပြန်ဖတ်တာပါလိအရင်တော့မထွက်တော့ဘူးနောက်ဆုံးတာမန်မြေကြီးရောနှောင်းနေတဲ့ဥစ္စာကြရင်ပြန်ထွက်လာမယ့်ကြီးဒီပို့ပြီးတော့နည်းလာမယ်နောက်ဆုံးရှင်သေးလိုပြင်လို့ကြရင်တော့ဖြစ်လာတယ်လုံးဝရိုးပြည့်ပြည့်နေတဲ့ကြောင့်ပြန်ဖတ်မဲ့ကြီးရှေ့ရတိုင်းရှေ့တဲ့ဥစ္စာတွေကြရင်နည်းသွားတယ်အဲ့ဒီတစ်ခုတစ်ခုချင်းကိုရေမျိုးစားလိုက်တစ်ခုချင်းဖြစ်တဲ့ဥစ္စာကိုသွားခဏခေါ်တဲ့အသုံးလုံးပေါ့ specific ကြီးလို့ကြီးကကျွန်တော်တို့ဒီမှာဒီမှာထွက်တဲ့ထုတ်ထွက်လုံးနဲ့တူပါပဲအဲ့တော့ပြန်ထွက်တဲ့လုံးပေါ့တစ်ခုချင်းရဲ့ဟုတ်အမှတော့ဟောတွေ့ပြီအဲ့တော့လေအဲ့တော့ရားရပါတစ်ခုလေးပြန်ဖို့ရတာပါလေသူရဲ့ပွားတဲ့ဥစ္စာပေါ့နော်အဲ့ porosity ကလည်းဘယ်တော့ပွားတယ်ဆိုတဲ့ဥစ္စာပြောတာရိုးမြေကြီးကပွားတာဘယ်လောက်ရှိလဲ55ရှိတယ်အဲ့ဆိုရင်ပြန်ထွက်တာ40အဲ့တော့သူဒီမှာကျန်တဲ့ဥစ္စာ55ဟုတ်ပြီနော်ဒီမှာကျန်တာရေကြီးကကြိုက်တယ်အဲ့ဒါလေးစက်ပြီးတော့ဒီပြကြတော့ရှုံးပါ55ပြန်ထွက်တာ200ရတယ်လို့ရှိတယ်သူ့မှာကတ်နေတာက48ဟုတ်ပြီနော်နောက်ပြီးတော့အဲ့ကြတော့ဆက်တာထွက်တာများလို့ဟုတ်ပြီနော်အဲ့လိုလည်းသွားတယ်သွားတဲ့ဥစ္စာမှာဟိုအနည်းဆုံးပါဖြစ်ပါလေဟုတ်တယ်ဗျာright စတင်ကြောက်ကတော့ပြက်သိပ်ဖြစ်နေတဲ့အကြောင်းဘယ်လိုထွက်ပါလဲအဲ့တော့ထွက်တာတော့ဟုတ်ပါဘူးနော် Yeah, I think they got somebody like this.
Yeah, so we can use this right now for our example. So what is the geology of this area? We need to know something about the type of material here. We're just going to assume something simple. But you see, if this is clay, we can pump the water down 10 meters we barely get any water. Only 2% of that 10 meters is actually water, right? Because the rest of it's trapped in the particles, right? Whereas if it's sand, we can pump it down 10 meters and 22% of that will be the equivalent of water, right? Or if it's limestone, a little bit less. Maybe if it's where is it? Sandstone or granite, very low. Because granite's very solid material. It's a igneous material, very low specific yields. Depends on the fractures and stuff. Okay. So what type of material should we use? Do you guys know the specific yield for Pelé, roughly? Maybe 0.2, 0.15. It's probably somewhere in the, maybe a mix of granite, sand, and gravel, like depending on where you are. Maybe these ones, you think? Maybe, or it depends on where you are. Sand, okay. So let's just use sand. We'll just make it easy. So sand, okay. So the specific yield, this is in percent. So 22%, so we're gonna make it like this. SY is equal to 0.22 or 22%. Okay. So what does that mean? Because the first idea was, okay, we just take the area, multiply it by delta H, and that gives us the volume, right? You can say volume, change in groundwater, right? Actually, let me just, I don't know why I'm using these symbols. Okay, let's just do it like this. Change in groundwater equals the area times the change in H times what do I need to multiply this by to get the actual volume of water? Yes, exactly. Okay. So what is it? Change in groundwater is equal to the area, 4560 kilometers squared, times delta H in kilometers. So 0.010 kilometers. Is that good? Times 0.22. Can someone tell me what that is? Do you have a calculator? Yeah, race. Should be like 10. And what's the unit? Okay, so now this number compared to precipitation is big or small? Yeah, it's almost how much bigger than precipitation? Right, it's almost double precipitation, right? So if in 1 year, we're making lots of assumptions. We don't know. I'm certain that the whole aquifer is not the same. And we know it's different. That's one thing. The other thing is it's not all sand. Okay, so we're making lots of assumptions. But if this aquifer were all sand, and it was all the same, if we saw 10 meters of decline in the water table in 1 year, we should be very worried. Wow, the precipitation is only 5 cubic kilometers, and we took 10 out from the ground. This is very unsustainable, right? We're pumping twice as much as what's coming in. Not good, right? So it is very unlikely that we would ever see 10 meters in 1 year like that. Okay, maybe we see 550 centimeters. You know, maybe we see, yeah. But I keep on using the metric because I feel like when I'm out of the U.S. I should use meters, but then you guys use meters as well. Okay, so yeah, this is unlikely to happen, and if it did, we should be very concerned. Okay. So what would the answer be if it was just 1 meter decline? What would the volume be? Just 1 meter. What would the, would just be 1 cubic mile, right? Okay. And that would be about 20% of our precipitation. Okay. Now the delta S, this ends up being delta S, right? For groundwater. If every single year, oh, and by the way, is it negative or positive? Is it's a decline, right? Or is it negative? If every year in our water accounting, so if we look at our water accounts, if every single year we see the storage going down, down, and down, and down, and down, and down, that is the sign of unsustainable use. The delta S should be 0 over time. Maybe some years it's positive, some years it's negative, but if it's always negative, like the water's always going down, 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 that means we're on a track. Like if you're in a plane, you're flying, if you're always going down, and there's no runway to land on, what's going to happen? Right? It's like groundwater has no runway. So if we're going down, we're going to crash. Groundwater, we want to stay up. Okay? Otherwise, it's not good. Okay? So that's how we might calculate the change in volume for groundwater. Okay? I think this is pretty easy theoretically. This is the key equation here. So it's the area, the change in height, and then the specific yield. Okay. Okay. So we're going to do this. We're going to do this think, pair, share thing for groundwater now. What I want you to study is, where is it? Yeah. For this, let's just broaden up a little bit. And let's say, look into any ways to measure a change in storage. So anything. It could be, again, 4 things. A way to measure the change in snow or ice, a way to change the measure of reservoirs. You can look at remote sensing, maybe there's a way. A way to measure changes in groundwater storage. What do we need to measure to know this type of thing? And then a soil moisture. Okay? So just take 10 or 15 minutes to learn as much as you can about these changes in storage and how we measure them.